So this forms a NOT gate, and here whenever my input is A, I'll get a inverted output which is represented as A dash. Just by placing a notch in front of a AND gate will be successfully called as a NAND gate. XOR gate is all about a gate that is having two inputs and one output. We can say only when both the inputs are of same, then the output will be high. Hello everyone, I welcome you all to the third session of Unit 3, that's under Digital Computer Organization, and Unit 3 is all about Boolean Algebra. This is a third session, and in our previous sessions we have discussed so many important things, so I request you to go back and check those sessions as well. Yeah, over here my name is Deepa Kutnikar. I am working as an assistant professor under Department of Computer Science, Vidhyaashram, Temple of Excellence, MYSURU. Let's see what is the thing that we have discussed in our previous session. In our previous session, we have discussed what is a K-map, and we have started learning from 3-variable K-map, and we also did discuss 4-variable K-maps too. So the K-map is not only with respect to SOP, but we have discussed with respect to POS format as well. And up next, we did also discuss the don't care conditions under K-map. So this is one of very interesting thing that we have discussed. So if you want to learn more regarding this, you have to check our previous session. In this session, we will be discussing regarding the basic gates, like what is a basic logic gate and what are the different types, and what are the different types of gates that are also called as derived gates, and there is something called as universal gates. I believe you know that. Let's learn regarding these things. Also, we will be learning the realization of basic gates using our universal gates, that is a NAND gate as well as a NOR gate. So let's start understanding from a basic gate, that is a NOT gate. Let's see the first gate, that is the first fundamental gate, which is all about a NOT gate. Yes, a NOT gate is also called as an inverter or inverting buffer, because here whatever the input you give, it will provide you an inverted output. So let's see, that's a logic symbol with respect to NOT gate. So it is like whenever you draw a diode, correct? It is very similar to a diode, but a notch included to that. So this forms a NOT gate, and here whenever my input is A, I'll get a inverted output which is represented as A dash. So let's see a small truth table with respect to this NOT gate. Whenever my input is 1, I'll get an output inverted, that is 0, and whenever the input A is 0, then the inverted output is 1. So this is nothing but a simple NOT gate, and this is one of very important gate that's under basic gates. So up next, the second basic gate is a AND gate. So here the AND gate, like here we will be having two inputs and we'll be having one output. When the output is high, yes, exactly, the output will be high only in one condition. That condition is whenever the inputs are high, only at that time the output will also be high. Okay, let's see a small logic diagram for this. So we have two inputs A and B, done, and this is a symbol or a logic diagram for our AND gate with respect to the truth table. So as we know, we have two inputs, that is A and B, and output X. Okay, this output is X, which is equal to A into B. Up next, let's have a truth table here. It is a 2-variable truth table, right? So 2 bits we are working with. So we will be getting 4 different combination, that is 0, 0, 1, 1, and with respect to B, we get a output of, the combination 0, 1, 0, 1. Up next, let's see a small output for this. So as I told, the output, that is 0 into 0, will give us an output of a 0. Followed by 0 into 1, yes, exactly, it's nothing but a 0. Up next, 1 into 0, 1 into 0 is also a 0. And 1 into 1, it gives us a value of 1. So that's what I had told you, like whenever our input bits are high, only at that time the output bit will be high. So this is a truth table with respect to AND gate. So now let's move forward and see the third basic gate, that is none other than a OR gate. We can say like the output state of a OR gate is high when at least one of input goes high. Alright, so even here we will be working with two inputs and one output. Whenever any one of these two inputs are high, then we can expect the output as high. Alright, so yes, let's see with a truth table. So we have two input, that is input A and input B. As it is a two input, we have four different combinations, that is 0, 0, 1, 1 and 0, 1, 0, 1. Now, what we have to write? Yes, the main thing what we have to note whenever we write a logic symbol is A plus B, okay? Alright, so now let's start adding 0 plus 0. It is a 0. Alright, 0 plus 1, what is it? 1, correct? 1 plus 0, again it's a 1. Done. 1 plus 1, even it gives us a value of 1. So this is a truth table of a OR gate. So this completes our basic gates. So let's recall the basic gates, that is first one is NOT gate, second one is an AND gate and third one is a OR gate. There is also something called as universal gates. These gates are called as universal gates because by using these gates you can implement other gates too. Alright, so that's why it is called as universal gate. And which are the two gates that are called as or termed as universal gates? Yes, it is none other than a NAND and NOR gate. So let's see like what is a NOR gate. We can say NOR gate is just an inverted form of OR gate, wherein like we will be getting a high output only when our two of the inputs goes low. So we have a basic representation over here. As we can see, there are two inputs, that is A and B, and we will be getting one output, that is Y. And yes, the output will be a complemented form of a OR gate. And here with respect to truth table, again as it's a two input, we have to go with four different combinations. So let's start 0, 0, 1, 1 followed by B, 0, 1, 0, 1. Alright, it's done. Now let's see how it works. It is A plus B whole bar, right? So let's see 0 plus 0. So only in this condition we will be getting a value high. Rest all the conditions will goes low. Or let me explain you in some other thing too. So this is a OR gate representation. So with respect to OR gate, that is A plus B. So what is 0 plus 0? It is none other than a 0, correct? And what is 0 plus 1? It is a 1. Okay, 1 plus 0, again it gives a 1. 1 plus 1, yes, it is a 1. So now you can see the OR gate as well as the NOR gate output, both are inverted, correct? Both are inverted. So if you check NOR gate, it is an inverted form of OR gate, or if you just hold NOR gate, then you can say the OR gate is an inverted form of our NOR gate. So thus is all about our first universal gate, that is a NOR gate. Up next, let's see what is a second universal gate. It is none other than a NAND gate. Even in this NAND gate, we have two inputs and one output. With respect to input, it is represented in the form of four different combinations, and we will be having one output bit. Alright, now let's see the symbol for NAND gate. As we know, a AND gate symbol is just this much, correct? A Y followed by 2-bit inputs. But just by placing a notch in front of a AND gate will be successfully called as a NAND gate. And you can see the representation. This AND gate is A into B, and with respect to NAND gate, it is A into B whole bar. Let's see the truth table for this. As we are having two inputs, we have to go with four different combinations. So let's start writing it. 0, 0, 1, 1 followed by 0, 1, 0, 1. All right. Now let's see when the bits are high. So for that, let's write our AND gate first. So this is our AND gate and this is a NAND gate 1. So when 0 into 0, it gives us a value of 0. Similarly, 0 into 1, again it's a 0. 1 into 0, 0. 1 into 1, 1. Alright. Now, as we know that NAND gate is a complemented form of AND gate, so let's directly complement it. So the complement of 0 is 1, complement of 0 is again 1, again it's a complement of 0, and for the last bit, it's a complement of 1. It is none other than a 0. So this is nothing but a NAND gate. So now we have completed basic gates and then we did completed universal gates. Up next, there is something also called as derived gates. So that derived gate is nothing but a XOR gate and a XNOR gate. So let's understand like what is this XOR gate. XOR gate is all about a gate that is having 2 inputs and 1 output. Now let's consider if my output has to be high, then the input should be unequal or uneven. Whenever my input goes like 0 or 1, that is like unequal combination, then only at that time the output will goes high. And whenever the inputs are same, that is either 0, 0 or 1, 1, then at that time the output will be low. So this is all about a XOR gate. With respect to practical applications, there are multiple practical applications which uses the XOR gate even in your daily life, that is the switches, the two-way switches what you use. When either of the switch is on, only at that time your bulb will glows or your appliances will work. At the time like when both the ways are high, at that time your appliances won't work, correct? So that is a complete practical application of a XOR gate. Absolutely, this is very, very important when you consider with respect to the realization of your gates, also with respect to the practical applications. So this is a symbol of a XOR gate where we get the expression for XOR gate is A dash B plus AB dash, which can be also written as A XOR B. Now let's see a truth table over here. As it has 2 inputs and 1 output, we have to go with 4 different combinations of input, that is 0, 0, 1, 1 followed by 0, 1 and again it's a 0, 1. Done. Now we have to write the output. So as you can see, both the inputs are same, that is 0, 0. So at that time the output will be 0. Up next, you can see here the input is unequal, that is 0 and 1. So the output goes high. Up next, 1 and 0. Even here the inputs are uneven. So the output will be 1 followed by 1 and 1. Both the inputs are same. So the output will be 0. So this is all about a XOR gate, and XOR gate is also called as a derived gate. So let's move forward and check the second derived gate, that is none other than a XNOR gate. XNOR gate is all about a combination of, or we can say inverted form of XOR gate. It is very, very simple. Like in XOR gate, what we were doing is we were writing a 1 or we were getting a high output only when one of the output or one of the input is unequal, correct? But here it's completely an inverted case. We can say only when both the inputs are of same, then the output will be high. So this XNOR gate is also called as a equivalence gate. Please note that this is also called as an equivalence gate. Alright, now let's go with a simple circuit. Here a XNOR gate followed by a notch in the front will give us a XNOR gate. So this is a second type of derived gate. Alright, so let's see what are the different inputs. We have 2 inputs, so we have to deal with 4 different combinations of input, that is 0, 0, 1, 1 followed by 0, 1, 0, 1. The output is, as I told, only when we have equal inputs, only at that time the output goes high. And at the rest of the time, the output goes low. 1, 1, both the inputs are high, so the output goes high. So this is all about derived gate, that is two different derived gates, XOR and XNOR. Till now we have studied three of the basic gates, that is NOT gate, AND gate and OR gate. Up next we did study the universal gate, that is a NAND and a NOR, and followed by the next type is a derived gate. So under derived gate we did discuss XOR gate and a XNOR gate. This was with respect to gates. Up next, let's head up with the implementation or realization of basic gates using universal gates. Alright, let's start here. This is with respect to the NAND gate. So a NAND gate symbol is none other than this, correct? We will be having two inputs, that is A and B, followed by one output. So this is a simple NAND gate. By using this universal NAND gate, now it's a time to derive the basic gates. So the first basic gate is none other than a NOT gate. Okay, so now let's see how the NOT gate can be represented by using a NAND gate. As we know, a AND gate has only one input, so we have to draw a symbol in this way in order to merge it. Like I don't have both symbols, both the inputs will go with a same, that is with respect to A. So this is how we can draw a NOT gate using NAND universal gate. Next, that is a AND gate. AND gate. So now let's see how to draw a AND gate by using a NAND gate. So for AND gate, we know we are having two inputs, that is A and B. Alright, up next, we have to draw a simple NAND gate. Yes, it starts with a simple NAND gate. So here, what is the output we are getting? It is A into B whole dash, correct? So now, what we have to do? We have to invert this, correct? So for that, let's add a NOT gate by using NAND gate, and this gives us a simplified form of a AND gate by using a universal NAND. Therefore, y equals AB bar whole bar. This gives us a value A into B. Alright, next third one, that is a OR gate. For OR gate, now let's see, we have two inputs, right? So that two inputs should start with a NOT gate by a NAND. So this is a and here I'll be getting a output, that is A dash. Let's follow one format of representation. Okay, we'll be getting a dash from here. Similarly, for B, I need to draw a AND gate. So here my output will be B dash. Alright, what we have to do is we have to again bring it together and draw one more NAND gate. So this gives a value, that is A bar, B bar, whole bar. So by De Morgan's theorem, we know that A dash into B dash whole dash can be written as A plus B. So this is how we can realize or implement three different basic gates. That's by using a universal NAND gate. Up next, let's see how to implement the derived gates, that is a XOR and XNOR gate by using a simple NAND gate. So yes, let's have a partition over here. Alright, this side, let's draw a XOR gate. So let's start drawing here. So we are having two inputs, correct? So the first input is A. So for that, the output will be A dash. This is the first stage. Next, let's also draw a gate B. Okay. This yields us B dash. Now what exactly we have to do is we have to add A dash and B with a NAND gate. So similarly, what we have to do is we have to add A with B bar. Okay. A with B bar. So now here the output will be, we are having A dash, then a B whole dash. Similarly, here we have A followed by B dash whole dash. Finally, what we have to do is we have to add this by using one more NAND gate. So by De Morgan's law, we can say this A dash B whole dash followed by A B bar whole bar will give us A dash B plus A B dash, which is nothing other than A XOR B. So this is with respect to XOR gate. Up next, let's see how to implement XNOR by using our NAND gate. Next is XNOR. Up next, let's see how to realize a XNOR gate by using a universal NAND gate. As we know, we are dealing with two of the inputs, that is A and B. Okay. And from here, let's draw a small NAND gate. With this output, what we get here is none other than AB whole bar, correct? Next, with this output, let's continue here drawing one more NAND gate where we will be yielding with A into AB whole bar followed by bar. Up next, similarly, we have to draw one more NAND gate here. So we can say here we will be getting AB whole bar into B dash a whole bar. Alright, the final step what we have to do is we have to consider this and draw a AND gate. Yes, A is all about implementation of XOR gate. So at the output, what we'll be getting is A into AB whole bar into AB whole bar into B whole bar. And again, by De Morgan's law, what we can expect here is A XOR B whole bar. So this is how we can implement a simple XNOR gate by using a universal NAND gate. So I believe you can understand now why this NAND gate and the NOR gate is also called as a universal gate. You can implement starting from basic towards the derived gate as well. So that's the ease of a universal gate. Now let's see how the basic gates are implemented using a NOR gate. Let's recall a simple NOR gate. So it is in this way. We'll be having two inputs and the output 1, that is none other than A plus B whole bar. Correct? So this is a simple NOR gate. Now we have to implement basic gates. So let's start doing that. First one is a NOT gate. As we know, we have only one input with respect to our NOT gate. So we have to combine and draw a NOR gate. Therefore, the output will be A dash. Up next, that's a AND gate. So the AND gate, in order to deal with this, we have to use a simple NOT gate for each and every input bit. So it becomes A bar and here it becomes B bar. So finally we have to add both of them, where it gives us a value that is A dash plus B dash whole dash, which is equal to A into B. That's by De Morgan's law. We can say that A dash plus B dash whole dash will be yielding us A into B. Next, third one, a simple OR gate. It is like, first we have to draw a basic NOR gate. Alright. So for this NOR gate, we are having two inputs, that is A and B. Done. Up next, what we have to do? We have to invert it. So let's use a simple NOT gate. This is how we can draw a simple OR gate by using, so here it's A plus B whole bar. So here it is A plus B whole bar, which gives us a value of A plus B. So this is how we can implement the basic gates by using our universal gate, that is a NOR gate. Alright. So let's head up and implement the derived gates by using the NOR gate. Now let's start with the first type of derived gate, that is none other than a XOR gate, which is also written as. So now let's start implementing that by using a simple NOR gate. Okay, so over here it's input A and B. Up next, what's that? So we have to pick the input and draw a simple XOR by using the stage. Alright, similarly, I have to pick one more here and let's draw one more OR gate. So yes, we have missed this. Let's write here. It will be A plus B whole bar, and here it will be A plus B whole bar. Similarly, it is B plus A plus B whole bar. Up next, what we have to do is we have to include both of this and draw a OR gate where the output of this will be a combination of both of this. But as we know, a XOR gate is nothing but A dash B plus A B dash, correct? So we need one more complement level gate. So yes. So this yields us A dash B plus A B dash, that is none other than A XOR B. So if we simplify this, we will be getting this A dash B plus A B dash. But for that, we have to again use a complement form. So here it is a combined form of A plus whole bar plus, I'll be writing it here, B plus A plus B whole dash. Alright, this is all about implementing a simple XOR gate by using our NOR gate. So the first derived gate is also realized. So let's head up with XNOR realization. That's by using a NOR gate. It's almost similar to our XOR gate, where there is no need to include this that is inverted gate at that last end. So let's start drawing that. A, B. So here we get A plus B whole bar. Up next, we have to draw a OR gate by using this, where the output is a plus of what is this? A plus b whole bar. All right. So similarly, again we have to redraw one more XNOR gate here, which gives us a value, that is b plus of this value, that is b plus of a plus b whole bar. Next, the final step, what we need to do here is we need to add one more NOR gate. So that's a final NOR gate. So yes, here it is a dash b plus a b dash whole dash, which is none other than a XOR b whole bar. This is how we can implement a XNOR gate by using our NOR gate, which is a universal gate. So this was with respect to today's session. Thank you.